Hello, and welcome to the Engineering 3100 design presentation, Removal of Microplastics from Sewage Sludge, presented by the Plastic Purge team.
Firstly, why do we want to remove microplastics from sewage sludge? Essentially, microplastics and microfibers from wash water collect in biosolids during wastewater treatment and become environmental, economic, and health hazards when they are applied as agricultural fertilizers, and we need to develop a technology to reduce the microplastic concentration in biosolid to mitigate these hazards. These hazards include microplastics and microfibers in soil reduce the soil's capacity to retain water, which would impact crop production and quality. The reduced crop production and/or quality could cause price inflation impacting consumers. There has been extensive research on the impact of microplastics and microfibers on aquatic ecosystems, such as ingestion of microplastics can inhibit organism development. Microplastic pollution is speculated to reduce tourism due to decreases in marine life biodiversity and populations, and microplastics impact human health mainly through inhalation, and chronic exposure can lead to asthma, autoimmune disease, and cardiac diseases.
Within the scope of this project, our objective is to design a process to reduce microplastic concentrations in sewage sludge. We focused on the reduction of microplastics in sewage sludge by firstly, reducing the number of microplastics and microfibers present in wastewater, and secondly, by incorporating a process to reduce microplastic content in sludge at the Toronto Ashbridges wastewater treatment plant. In this diagram, everything highlighted in red is within the focus of our scope.
Our solution must improve the quality of the sludge by lowering the microplastic content with no toxic residues from the treatment or negative impact to the nutrient levels. The solution must follow existing regulations for Ontario compost quality and conform with the plant nutrient management strategies. There are 4 categories criteria to optimize this design. Optimizing the solution is defined as maximizing the percentage of microplastic removed, the size range captured, and minimizing the retention and process times. Minimizing the cost of the solution is to minimize the capital, operation, and recurring material cost. Minimizing additional environmental impact refers to minimizing the energy and maximizing the sludge quality. Health and safety considerations focus on minimizing operating risk and reducing the risk of harm from microplastic aerosols. With these defined, we can look at our solution.
The Plastic Purge team used a 6-step engineering method consisting of identifying the engineering problem, defining the problem constraints and criteria, planning by creating schedules and dividing tasks, and designing the process using schematics and calculations. The development and launch steps were omitted due to constraints in available time and resources.
The preliminary design consisted of a domestic filter and oil extraction protocol process integrated into existing wastewater treatment plant primary clarifiers. The final design has integrated an API separator to help further reduce microplastic concentrations in wastewater and sludge. A rotary drum vacuum filtration system was added so that the oil from the oil extraction protocol may be recovered and reused. The domestic filter has included an additional valve in the event of overflow, and the outlet has been moved directly to the bottom of the device to prevent bacterial growth from stagnant water. These are the online tools that the Plastic Purge team used to develop the design process. This includes Microsoft Office 365, SolidWorks, and AutoCAD. Omni and Google Scholar were used as databases to find research and information. Next, we will discuss the finalized design solution built from these tools.
Our solution is a process design using a combination of a domestic filter and oil extraction protocol within the wastewater treatment plant to remove microplastics from sludge.
So moving on to the domestic filters, these filters are mainly intended for washing machines, specifically for top loading and side loading ones. The filters do not require any energy inputted into them as they are a completely passive product and only require the drained water from washing machines to properly function. The filters are small and they can be easily installed on the sides of washing machines or nearby walls. The filters are also very low on environmental impacts. They can also be changed pretty easily and relatively quickly. Also, the filters can notify the user when any maintenance or service is needed on the system. The filter is also made of reinforced polypropylene for the outer cartridge, as it provides strong structural support, and polypropylene for the filter membrane, as the polypropylene can provide very good filtration characteristics. Moving on to the 2D drawings of the filter cartridge will have a height of 310 millimeters, while its width will be 130 millimeters. The filter membrane will have a height of 308 millimeters, and its width will be 130 millimeters. To to the right is displayed as the physical representation of how our filter would actually look, with the right side having the inlet and the bottom left side having the outlet. Inside is a filter membrane, which is highlighted in blue, which is placed directly in the middle of the filter cartridge. And the sensor, which is right under the lid, is on the right side towards the inlet. The sensor is attached to cables, which is connected to a battery pack. And inside this battery pack is a speaker system. The filter also has a handle on the top of the lid to provide ease of access to the user when replacing the filter membrane.
Oil extraction protocol, or OEP, is an effective, cost and time-efficient laboratory method to separate microplastics from environmental matrices. It works by adding oil to a diluted sediment or sludge sample, mixing, and then leaving to settle before separating the oil for isolation of microplastics. OEP is a density-independent method, meaning it uses lipophilic and hydrophobic properties of plastic for separation. When mixed, oil will coat the surface of the microplastic and make it float to the top of the mixture. Therefore, it works for all types and shapes of plastic. Organic matter does not interfere with the process, and it doesn't include any chemicals harmful to humans or the environment. This makes this method ideal to upscale for application in the wastewater treatment plant. Our design to integrate OEP into the wastewater treatment plant is a continuous process and makes use of pre-existing infrastructure such as the primary clarifier. First, canola oil is pumped into the wastewater and thoroughly mixed in a static mixer before reaching the primary clarifier, where the oil will be skimmed off the top with the rest of the scum. Effluent from this unit will then pass through an API separator in order to remove even more of the oil. The scum and oil waste streams from these processes are then directed towards the rotary drum vacuum filter. Here, the filter cake of scum and microplastics can be sent for disposal or other processing, whereas the filtered oil is pumped back into the influent.
The domestic filter is the first component of the design solution, which reduces the microplastic concentration in the wastewater. The effluent from washing machine will flow into the filter from the inlet, from which the microplastics will be captured by the filter membrane, which can remove up to 90% of microplastics, as low as 50 micrometers in size. The water level will rise as the microplastics build up on the inlet side of the membrane, as the water flows through and drains away from the outlet. The membrane can approximately last up to 37 washes, until it needs replacement. An overflow prevention system is implemented such that when the water reaches the overflow prevention area, it will flow over the membrane and drain out from the outlet at the bottom of the filter. Once the water level on the inlet side gets close to the overflow region, the flow switch sensor will notify the user via a speaker. The user then must replace the filter membrane as soon as possible.
The functionality of OEP is proven through several technical calculations. It was determined that adequate mixing and dispersion of oil is achieved in the static mixer through the calculation of Reynolds number, which showed turbulent flow. The analysis of oil droplet size and rise time proves that the oil has not emulsified and is able to separate in time for skimming in the primary clarifier and in the API separator. Mass balances were used to determine volumes of waste streams for subsequent processes, such as the rotary drum vacuum filtration, which is also deemed feasible due to the calculated filtration area and power requirements. These requirements are comparable to other industrial rotary drum vacuum filters.
The domestic filter is 90% effective and treats 33.3% of the microplastics that enter the plant, causing a 24.6% reduction in the microplastic for all of the sludge. The OEP method alone leads to an 86.32% reduction of microplastic, as canola oil binds to 96.2% microplastics, and the removal efficiency rate are 61% and 75% from the primary clarifier and the API. For filtering into the rotary drum, that is 90% effective at removing the microplastic from the oil. Combining 82% filter use uptake, as cited from a consumer poll, with one line of primary clarifier, we get a 96.5% reduction in the OEP treated sludge, which makes up 3.66% of plant sludge. The filter uptake as low as 20% would allow our target of 95% microplastic reduction in our treated sludge. If all 6 small primary clarifiers at the Ashbridges Water Treatment Plant in Toronto are fitted with OEP, 21.9% of the plant sludge would be significantly lower in microplastic. This could make up the entire 18.4% of wet sludge that is applied annually to agriculture fields. So our design works, but is it safe? Safety features of this domestic filter are the overflow prevention and alert system and the drain design to prevent water pooling, thus discouraging microbial growth, as Ali discussed. E. coli is our main microbe of concern in the OEP system, and despite the inhibited replication of E. coli in canola oil, we will change the oil every 7 days. This aligns with the Ontario Guideline for Sewage Works, Sludge Storage and Disposal. The presence of any undigested oil in the sludge when it is heat treated was a fire concern, but the thermal treatment temperatures are well below the canola flashpoint level. The treated sludge is expected to meet Ontario compost standards once it undergoes existing treatments in the plant, so it will be considered ecologically safe for land application. All of the equipment selected is compliant with the Ontario Health and Safety Act and will be installed in a complying manner, including using machine guards.
With filters on 82% of washers, the system removed 96.5% of the microplastics in the sludge, while also reducing the microplastics in the water effluent by 35.5%. This will significantly reduce the amount of microplastics that end up in the agricultural soil and the ocean. This will also result in better soil quality, which may improve the quality of the crop yields and benefit the farmers that use the sludge from the wastewater treatment plants. Also, the reduction in microplastic pollution in the ocean will reduce the impact on the aquatic life.
Moving on to the economics of our solutions, the capital costs for both the solutions will be $496,822.18, while the operating costs will be $226,961.63 per year. For both these solutions, there will be a reduction in any possible crop reduction and damage from the microplastics, which could provide much healthier and increased crop yields. This would ultimately lead to the crop selling prices being much lower. Also, through these solutions, the healthcare costs would be much lower, as the potential for the microplastics to cause cancer will be significantly reduced since there will be much less microplastics present. Also, the soil quality will be significantly increased, as the sludge quality will increase, since our solution would have much less microplastics present in the sludge, which would eliminate the possibility for the farmers to provide extra care to their crops, which would lead to increased costs.
There are several uncertainties in our design, especially within our calculations. There is uncertainty due to ranges for material properties, such as oil, sludge, and scum density. These variations in properties have a little effect on the results. However, ranges for filter properties, such as specific cake resistance, have a large effect on results. There is also uncertainty with assumptions for givens and initial conditions, such as microplastic concentration in wastewater, as this value was not specific to Toronto. The estimated design cost has large uncertainty, as some equipment will need to be custom made, and it is difficult to get an accurate estimate without a quote. Therefore, due to these multiple uncertainties, a pilot scale testing is needed to determine specifications and ensure functionality.
In conclusion, our goal is to reduce the concentration of microplastics and microfibers in the wastewater and the sewage sludge at the wastewater treatment plants, which have a significant impact on the environment. Our final engineering design solution consists of a domestic filter, an oil extraction protocol, an API for increasing MP removal, and a rotary drum vacuum filter. Finally, the design has a microfiber removal efficiency of 96.5%, which is ideal. Plastic Purge should be developing a plan that involves implementation of the design to investigate and confirm the efficiency of the engineering solution. A life cycle analysis should be conducted to assess the design components' environmental impacts. Finally, a business plan must be established to practically implement the design at wastewater treatment plants in Ontario. This concludes our presentation, and thank you for listening.